especially with the U.S. Air Force Academy down south. They have some tremendous experimental facilities for doing gas turbine engines, so we'd like to work with them component by component. So just studying the fan first, are we getting that correct? And again, as you go along this process, it's still verification, and this is getting more into validation. You validate each of these components as you're going along, so it should be correct. The real challenge is just being able to do that, being able to do a full engine simulation of a gas turbine on a computer. Nobody can do that right now. I mean, not with LES anyways. It's just, I would say, you need higher order accuracy. You need to get those grid sizes down, and you need the performance work too. You need to be able to use the CPUs and GPUs effectively, and if you can't do that, then
the physics is so rich. Like we talked about the shock waves near the blades, possibly with combustion, and then LES still kind of models the smaller scales of turbulence. So even if we do it, like even if the whole simulation is done and you do it, how the validation, I guess, still relies on the accuracy of the modeling that went into the basic LES itself. So yeah, I'm just wondering, like, what would be the net benefit of going to all this when you're still limited with the basic physical model itself cuts off a lot of the small scale physics and models it, and we go into all this fourth quarter.
There's still a lot more you can do with just LES. I mean, it's a matter of practicality. If you could do DNS everywhere cheaply.
So my question is really like, what is the practical benefit than just doing experiments with the pilot pushing the throttle and then seeing exactly whether
Design work or optimization work. That's what they did back in the 50s, right? Just experiments. But it's expensive. CFD, using computational methods, you still need to do experiments to at least validate what you're getting out of the CFD. But a lot of the times, the example of the wing design for these transonic wings, the CFD codes are very, very good now at designing an optimized wing for some given flow condition. We still need to do one wind tunnel test to make sure, or maybe two, to make sure that is the optimal condition, that CFD code is getting the right thing. But you don't have to do all your design work in the wind tunnel itself, which could be quite expensive. So we do always need that experiment. But if you have the capability in your CFD solver, it vastly increases the design and optimization, the amount of engineering you can do, and the fidelity of that engineering. So to answer your question, on the scale of turbulence modeling between RANS and DNS, when you're doing design work, you want the stuff as cheap as possible in terms of cost. And LES is kind of a middle ground where there are benefits. There's not benefits for every problem. Doing this transonic wing, you're not going to necessarily see benefits at the design condition of the wing. You might see a benefit if you have vortices coming off the wing, and you need to resolve that. For that inlet problem I showed, you can't really get that right if you don't do LES. You can get close with RANs, but not quite as high fidelity as we would like to be. So there is a definite benefit to getting to that next stage LES. And that next stage LES is not cheap either.
I understand that there will be a finite benefit. It's just that how significant is that?
I think it's tremendously important. Like Boeing has this problem right now with this inlet. They're getting bigger and bigger. These fans are getting bigger. What are they going to do? Their choices.
Did they have a story or what is they're already making or designing their engine, and is there some failure or some issue that's making them want you to do this whole simulation? So what is the benefit itself?
Like you might say, 11 feet fans right now work with RANs.
Yeah,
but could you do, will LES let them go to 12 feet or 13 feet?
It's actually a problem they never had to worry about before. And so they didn't have the capability. They didn't have the experimental facilities. They didn't have the numerical capabilities to actually solve this problem because they didn't have it. When the fans were small enough, they didn't have to worry about it. The engine manufacturers never put a constraint on them at what was the flow coming into the inlet. But nowadays, the engine companies are putting more constraints. So there's a new problem that they have to solve, and they have to invest in this one way or another. They're looking at investing in experimental facilities to help with this because they know this problem's not going away. It's staying around, and they're investing in computational stuff. So yes, they're come to us to solve this problem because they have to address it. I don't know if that answers your
It sounds like
question.
it's hard to quantify. It's like, that's what it's like, are they going to get their money's worth for another 20 years or 40 years? Are we going to have to hire another Stephen in 50 years or 5 years to do the direct?
It depends how far you push the engineering. I mean, there's a limit to all the models in the CFD simulations. It's not perfect until you're doing molecular dynamics of the atoms.
I mean, another example, I mean, so in the work we use this Converge commercial code extensively, and it's a 3D transient, we can inject diesel fuel in there, we've got detailed kinetics, but we're at the limit is what we can do with RAMs, right? And, but they do have an LES capability, but it will take us a month to do one
Yeah.
application. But some of your work, and I think, there may be ways to speed up the LES and that. So I would just encourage you to, the internal combustion engine. That's a good example where I think it's not quite, the geometry is not as sophisticated, right? But it's a 3D, system, and the industry is interested in it. And I think there might be some real applications here for some of your algorithms to do LES in that configuration, solve problems that we can't solve right now with fans. So I know you guys are working in that area as well, but I think that could be something that we can accomplish, maybe even accomplish in the next 3 to 5 years or not.
That's kind of what we're going after, yes.
I think that would be a strong new alliance,
Right.
and very relevant as well. Like there are experimental facilities right here on campus.
And it's kind of ideal, too, because natural gas engines, you remove some of the complex physics of spray modeling and stuff, so you can get in there without actually having to worry.
Well, we're doing dual fuel.
I know you are, and we'll get there, too, but just to start with.
We have some more questions in the back. Maybe we could do some other.
So you mentioned about how you're having some of the students in 342 do numerical calculations of ODEs and PDEs. I sort of have two questions around this. One is, what changes do you think would you recommend to our existing curriculum so they can be more prepared, so the students have so only the students that would get it have to come to recitation rounds, so basically all the students would understand. So then the second question is what do you think would be a good outcome for undergraduate students that leave here and work in industry in terms of understanding the complexities of numerical methods?
My opinion is, I think it's the wrong idea to take out programming from engineers. We all learned this in the 90s. I think it's a fundamental skill set, and I don't really agree with removing it. It was kind of interesting when I was teaching them with MATLAB, because MATLAB is a kind of a strange programming environment in terms of it hides a lot of the features of what's going on behind the scenes. You can just have kind of arrays that you don't really have to define their size or anything or what their elements are. It just kind of keeps up with you, except when it doesn't and it breaks, and then the students don't know really what the hell is going on. And they also saw just like fundamental mistakes. They don't really understand what's a function for, where does the program start. These are I taught this once, tried to do this, and I learned a lot myself of what not to do. Classic mistake was having them work on the command line and just run some functions from there, because then they don't get a clean definition of where the program actually starts. So that's something that they were confused about all the way through to the end. Other things, just like what is a variable? I have them signing f bracket a on the left-hand side equals something, which doesn't make any sense. They don't have the fundamental understanding of how data is stored in a computer. And I think all of this stuff is missed when you don't give them that fundamental course.
I guess, yeah, so what would you recommend for?
So I'm getting it. So, I would recommend a fundamental programming course like we had and scientific computing, to build on these fundamentals. Now, there are probably, there's competing interests in the department of, what are we actually going to teach them? And if this doesn't win out, I think there's other solutions too.
But the thing that we do is we teach them this at the freshman level, which is the stupidest thing in the world. We need to kind of figure out a way to integrate people in our classes, or have a class at the student level that's like this. Because like Rudy Stangelmeyer years ago introduced this concept of using like Excel to solve a partial differential equation. We get the EPO from it. And I still do it today, and it works out great. But then if they could then go to a class with Stephen or Shinpeng or somebody else, or Roshi, and solve it like numerical simulation type manner, then they really have that tool burned into their brain. It's the same thing we do with calculus. We teach them calculus before they even ever have to apply it, and then by the time you get them to apply it, they're going, oh shit, I wish you would have told me that when I was learning, because I would have learned it. So I don't know how to, that's my gripe. I'm sorry, Todd, to interrupt you.
I kind of have the opinion too that if you're very careful, you can integrate these components into existing classes and give them enough experience by the time they graduate. I don't know how to get the fundamentals of programming.
But to do that, we all have to cooperate.
But we'd all have to cooperate. And we're kind of doing that too. If everybody focuses on MATLAB, at least we can concentrate on one tool, make sure they have a decent understanding of how it works. I think they need more fundamentals at the starting point. But then we can gradually build up some of the core scientific computing ideas. And these are all your standard stuff. How do you do interpolations? How do you do...
Well, let me interject with Todd here. Says the PD tool in MATLAB is really cool. They actually have heat transfer problems that you can solve in that tool, and then they have videos online that you can watch. And it's really interesting to do it. I mean, you can do time varying problems and just steady state problems. And it's really interesting. But could we film you?
Do you think
could we film
it's
you?
a better solution, Stephen, to basically every junior and senior level class, from mechanics, structural mechanics to fluid mechanics to thermodynamics to heat transfer, to incorporate some sort of common language programming element?
Yes.
Or is it better to have a separate course that basically they learn all the programming tools and then professors?
I think in this era of, same when Professor Wepner came over here and gave his talk, computers are just becoming more important, and our engineers need to understand how to use these tools. MATLAB is widely used in industry. I think it would really serve them well to have a separate course just teaching the fundamentals of how programming works and introducing a lot of the concepts on numerical methods that are used in engineering, and then applying those, reinforcing those concepts throughout the rest of their curriculum. Now, I think you can get away with not doing that. I don't think it's ideal. My opinion is no, you should have a separate course. If you don't have that, I think we can still compromise and get something working, but...
A separate intro course?
No, a separate course on programming and scientific computing itself.
And again, I think that's fine, but it's like, could we film you when you do the stuff for fluids and then have the students watch it? Because if they don't go to recitation, they could probably get it out of watching the film.
Well, that was Todd's other question is, can you get away from the recitation? And even without any of the numerical stuff, I think fluids really needs a recitation. One of the reasons for that is because they've been exposed to so fluids is really an opportunity to apply the math they've learned in calculus and really understand it. They take it in calculus and they have no idea about vector calculus or really what's going on. It's just too abstract. Fluids, we finally use it and we can give it meaning then. What is the divergence of something? You can actually see it in the fluids. And
we have the honors fluids class. Maybe we say in the honors class we enrich it with this, and then only a third of the class or quarters getting the material. But
I think they all need it, and I think that I don't know. I think fluids is a pretty challenging class, dealing with pretty complex equations, fairly abstract, not as hands-on, difficult concepts like vorticity, and the students who came to my recitation, the ones who could, benefited tremendously. So why are we not giving it to them, is my opinion. I'm willing to make the time for it. And I think I can do just so much more when I have that too. That's just my opinion. I know there's other pressures too, but.
I've got one question, just in a slightly different theme. So I really enjoyed your talk, thank you. A sort of comment and a question. The talk, maybe I'm wrong, and this is the subject of the question, felt like it sort of represented the overall work from your group, and maybe Professor Gao would give a similar talk. And so the question is simply to differentiate your role within the group,
Right.
The department needs to make some decisions where we need to understand individual roles.
So yes, Shinfeng and I collaborate very closely, and actually you want this, I think, in a university. And a case study you might be looking at Dmitry Mavropoulos up at Wyoming. And he's had a very successful career with NASA. He's in a much better position than we're in terms of he had base codes to take from NASA and bring to his group. But he still works with another professor there on the same code base to even just move it forward and be able to accomplish more. So it really helps to have that kind of collaboration, I guess, within a group. So where does Shinfeng and I differentiate then? It's largely in the kinds of problems we're interested in solving. So look at a gas turbine engine. I'll take the fan. Shinfeng's going to do the combustor. It's kind of a question of physics. Algorithms, we're kind of both the same. We both get our hands dirty with the CFD algorithms itself. But if you look at the multidisciplinary chart of what it takes to do computational fluid dynamics nowadays, you need mathematics, you need engineering, and you need some computer science as well. Shinfeng will take on, just talking about this chart, Shinfeng will take on more of the mathematics side, so looking at things like the stability of the partial differential equations. I'll take more of the computer science side, looking at the performance of them. And we probably both do the engineering about equally. In terms of the physics themselves, I'm really interested in geometry. Almost everything that's coming into this code about geometry is me. It's my research. Shinfeng is really interested in physics. Anything to do with combustion especially is entirely her domain. And so right now we're kind of working together to get up this base capability, but you'll see us diverge a little bit more when we get into solving turbofan and solving combustor. And a lot of Shinfeng's research is too just on the fundamental models, computational models for combustion. And that's an area that I really don't get into either. I spend more time doing the performance stuff instead of that.
And at one point, I think it also answers the precise question as well. First, you mentioned that, okay, you do this LES, how do you know the knowledge correct? So basically, one part of my research is DNS, proton DNS. So we do this fundamental physics studies, active models, and feed it to LES. So feed it to this one. And then you say, okay, now, how does this compare, right? And then we kind of the LES, give me input, and I say, okay, this kind of coordination is not right, the model is not correct, and then more this DNS and other stuff. So I focus on this very physics models, turbulence and combustion reactions. This is the main direction. Also, I go more to apply the mathematics.
So it's a very important question, and there's three ways to differentiate. One is this chart. So Shinfeng does more mathematics, I do more computer science. The other is the problems we're after. Shinfeng's after combustion, I'm after geometry. And taking that then looking at what we're applying it to, I'm doing the fan itself, Shinfeng's doing the combustion chamber.
Right.
But of course, if we do something like a gas piston engine,
Sure.
there's
I'm all for collaboration and interaction. It's important that we have some understanding of
and
where you both
if those three ideas there kind of help cement that idea, I think. Yeah.
That's helpful.
And you always say the fan, do you also mean the nacelle and everything else?
Yes.
Is that all solved, and so that's not really the complication, it's really the moving
Well,
kind of solid boundaries? Why do you always say the fan? I'm just curious.
well, yeah, it's the moving part that's
That's complicated.
really a challenge. Yeah. I guess that's what I'm talking about when I say that.
12:30, so Sue asked me to stop. 12:30. And also just to thank Stephen and thank all of you for coming and follow up. I would say any questions that we didn't get to here, follow up and clarify these things.
I'm happy to hang out longer and answer questions if anybody has any more.